All right, hello everyone. Andrea and I are going to demo Docker112, and we're just tremendously excited about this. Here's what we're going to do. We're going to show you how to set up a swarm, which is we're going to show a 3-node cluster, and then we're going to show you how to deploy services on that swarm. And the recurring theme during this talk is going to be that there's a lot of sophisticated functionality like security, networking, orchestration, scheduling, that is exposed to the user through very simple CLI commands. And we're going to see that. So, Andrea, why don't we get started and start a swarm?
Sure. So I have a brand new machine here where the only thing I have up and running is Docker. So I'm going to go ahead and initialize my first swarm. All I have to do, pretty much, is to type Docker Swarm init. And that's it. I have a swarm up and running. So there's one node right now. There's a as you can see in the visualizer, we have a swarm up and running with one node. So to make things a little more interesting, I'm going to add a few extra nodes onto the swarm. So let me SSH into node 2. Again, it's the same kind of machine. There's just Docker, nothing else. And I'm going to type Docker Swarm join and point it to the original node. OK, this one joined. I'll repeat the same operation with the third node. And you'll see on the visualizer an extra node appearing. And that's it. I have a 3-node cluster.
So what Andrea just did was run basically 2 commands, Docker Swarm init and Docker Swarm join. You'll notice that what he didn't do was run any security-related commands. And that's a key point that I want to focus on. Security happens completely out of the box by default. So this swarm that Andrea has created has end-to-end encryption for both application traffic and management traffic. It has TLS mutual authentication. It has certificate rotation, which is very hard to get right. And we've given you sensible defaults in the platform. And lastly, it has this notion that Solomon mentioned of a cryptographic node identity. Let me try to explain the value of that. Suppose you want to segregate workloads on your cluster. Think about payment cards, for example. You want payment card workloads to go to only a certain set of nodes. So by giving each node a cryptographic identity, you can be sure that when you dispatch a payment card workload, it'll go to only those nodes that you've audited and gone through the appropriate processes to handle payment card data. So those security features happened all completely automatically. Now, I'd like to turn to the concept of services, because this is a new abstraction that we're introducing in Docker112, and it's very powerful. I think everyone or most people in this room are going to be familiar with the Docker run command. You type Docker run and an image name, and the Docker engine will start up a container based on that image. OK, that's great if you want to run single containers. But what we've done in Docker112 is introduce a new subcommand called Docker service. And what Docker service will do is start a replicated set of containers. And not only that, it will enforce a desired versus actual state reconciliation. So when you type Docker service, you're declaring a desired state for your service, and the engine will then fight to maintain that desired state, even in the face of machine failures and other kinds of system failures. So, Andrea, why don't we try to launch a service and see what happens?
Yep. So Docker112 introduces a brand new command named Docker service, which allows you to create, update, and control your services. So the syntax is going to look very familiar, since it's pretty much the same syntax as Docker run. So I'm going to name my service vote, and I'm going to deploy the service we just saw in the previous demo. So the InstaVote application. And I'm also going to expose a port so I can access that service. And that's it. As I type service list, I see my service up and running here. And vote. So we can see that we have one container, and it got launched to node 1. So let's check it out. Browser here. I'm going to open node 1, port 8080, and the application loads. So So as you can see here, this web page is being served by a container named B3 something something. The interesting part now is that I can go to any machine in the swarm. So let's take node 2, same port, and the same page is actually loading, being served by the same container, and that's thanks to a built-in routing mesh.
Yeah, so this routing mesh technology, yeah. This routing mesh technology is actually even more powerful than I think what we've seen so far. Because what's going on behind the scenes is we're allocating a cluster-wide port, and then we're mapping that port to the containers of a service. And in this case, there's only one instance of the service. There could be 100, 1,000, any number. And the routing mesh will take care of routing traffic to the containers of that service by exposing a port on every node in the swarm. So let's look at why is that interesting? Why is that important? Well, typically in an application like this, you would put an external load balancer in front of it. You would put an Amazon ELB, F5 in an enterprise, an Azure load balancer. All of these are host-aware load balancers. They're not container-aware. But because of this routing mesh, what we're essentially allowing you to do is use these legacy load balancers, non-container-aware load balancers, in order to load balance your containerized application. So that's something we're just very excited about. OK, Andrea, why don't we take a look at service scaling? How do I scale up?
Yeah, so it's pretty simple. There's a command named Docker service scale. So you just put the service you want to scale and the number of instances. This will instruct the system to start reconciling the states. So since I have just one container up and running right now, this will force the system to spawn 5 additional containers. And you'll see in a second the visualizer, on the visualizer, those containers spawning. So if I go back here and list the containers for vote, you'll see that I now have 6 containers up and running, and they're running on all the nodes. So by default, we use a spread strategy. Therefore, we try to equalize the load on the swarm. And in this case, since we scale to 6 with 3 nodes, we now have 2 containers per machine. So if I go back on the browser here and refresh, you'll notice that the container ID, every time I hit refresh, is changing. And that's because we have a built-in load balancer that performs round robin.
And I just want to point out that this actually illustrates what I was talking about earlier about desired versus actual state reconciliation. In this case, you'll see that he declared initially, we had an actual state of 1 container for this service. Andrea then declared a new desired state. He wanted 6 containers for the service. And that was all he did. The engine itself then took care of detecting a deviation between the actual and desired state. And in response to that, it started 5 new containers. It updated the internal load balancer configuration. All of this happened without any manual operator intervention. So again, an example of how we're making it easy to do things that in other systems or homegrown systems are very manual, very difficult to do. Andrea, why don't we look at how we would update the application source code if we had a new version of the app?
Yeah. So again, Docker service can help me do that. So there's a command named Docker service update, and it allows me to change any field I want of a service. So I could use that to change the environment variables, the ports, the volumes, the labels, or whatnot. In this case, I'm going to use it to change at runtime the image of the service. And that's typically what you want to do when you want to go from one version to another version of an image. So let's update the vote service, and again, insta-vote vote. This time, though, I'm going to select a different tag, so movies. As I do this, you'll see in the visualizer that all containers are brought down and then back up with a new version. So that's represented by a different color, the brownish. As I refresh, you can see that the changes were immediately picked up, and now I can vote on movies rather than cats and dogs.
So that was very cool. We just saw what I would call a lockstep update. Every container updated simultaneously. But in a real production environment, you would typically want to do a more advanced deployment strategy for new versions. A rolling update, for example, so that you can detect if something's going wrong and roll back before you've updated your entire application. Andrea, can you show us rolling updates?
Yeah, same command. Let's pick like a different image. So all I have to do is pass a couple of extra options to instruct the system. So I'm going to use update parallelism to set the number of containers I want to update at the same time. Let's say 2. And update delay to put delay between the updates. So by combining those two options, I'm instructing the system to update containers 2 at a time and wait 10 seconds between updates. So you'll see in the visualizer 2 containers going down, being brought up with a new color, and now there's a delay of 10 seconds. As I refresh, you'll see that the new version is showing up. And we're being balanced between the 2 versions, since right now the cluster state is being updated. And eventually, all containers are going to be updated, and I'm constantly going to get back the newer version of tabs versus spaces.
Yeah, so in a real-world scenario, obviously, you would want a longer delay so that you can roll out 2 containers, see what happens, and then have the potential to roll back. But the fundamental primitive is here, and that's really what Docker 112 orchestration is about. We're giving you the primitives that you need to do the operation scenarios that most people want to do. The last thing I want to turn to is what we call the self-healing properties of the system. Basically, its tolerance to failure. Because one of the fundamental design principles when we started on this project was we wanted to have a system that could tolerate any hardware failure and still continue to serve an application with 0 downtime. So think about a machine failure, maybe an entire rack goes down, a network switch starts malfunctioning and needs to be rebooted. All of these scenarios are happening just all the time. And instead of having to have the operator manually intervene every time one of these failures happens, why don't we have a system that's resilient against those failures? So in order to demonstrate these self-healing properties, Andrea, may I ask you to wound the system?
My pleasure. So I'm going to pick a random node, let's say node 3, which has currently 2 containers running. And I'm just going to brutally shut it down. OK. So the machine is now shutting down, and the system is pinging that machine. And soon enough, it will realize that the machine went down. It will flag it as such. So on the visualizer, we'll see in a second the node going from green to red. Here it is. And the scheduler will then suddenly realize that there are 2 containers running on that machine, and will migrate them to a different machine. So now we just saw the containers migrating back to node 2. And thank you. And I can refresh the service. It's still up and running. So I just brought down a machine live and with 0 downtime.
Yeah. Yeah, quite impressive. There was no application downtime. As far as end users of this application are concerned, nothing happened. So that's where we want to conclude the demo. We've barely scratched the surface in these 10 to 12 minutes, but I hope we've given you a taste. Andrea and I will be doing a breakout session at 11:45. You can come. We'll go deeper. Please bring your most difficult questions. I know some folks in the audience, I know some of you love to ask really tough questions. Please bring it. We would be disappointed if you did anything less. And we're just so excited to present this. So.
Thank you.
Thank you.
Nice. Maybe another round of applause for Mike and Andrea.